So I'm taping these lectures and putting Canvas, and they might be okay or not. So if you miss something, they will be there. If you happen to miss the class, they will be there too. So that's good. On a second note, I haven't yet. Did somebody try to do the Master in Astronomy accessible? Did you get it?
Unfortunately, no, because apparently there's a. Hang on, so. Oh, yeah, because last time there was some problems. There's one they said like you need like a class ID something like that.
That is the NA, that big number, NA battalion and a number. All in capital. Did you try?
I tried this one, but
You didn't get it? The book rep emailed me, and I haven't opened her email yet, so I don't know what it is. There is something going on. That's why I want to check with you. So I will work with her over the weekend to figure out the clicker change using learning catalytics. I think it's going to be fine, but just be patient and we will get there. So chapter 3 has some very nice historical development of astronomy to the point that we've hit 1600. So we went from a worldview that the belief was Earth happened to be in the center of the universe because that's what we see, that's what we perceive. I mean, we see stars, we see planets all rise in the east and set in the west, and they repeat this pattern on and on and on, and then we can divide what we see in two main types of motion: Earth spinning around its axis of rotation and Earth revolution around the sun. So this was well observed, but the interpretation was that, well, Earth, if we place Earth in the center of the universe, and there were very compelling arguments for that in 500 BC. The main one is, well, that's what we see, and Earth. If Earth is moving, how come we don't shake? If you put yourself in a cart and you put the cart to move, you're gonna feel some shaking, and we don't feel shaking. Second of all, if the cart is moving, put your head outside, you're gonna feel the wind blowing. How come the wind's not blowing as Earth goes through its rotation and revolution around the sun? So the argument was geocentric worldview is good. Now, by that time, church took that argument and used to support some poetical interpretation, in my opinion, that existed in the Bible. Earth was in the center of the universe, and upon which God has built its church, something like that. I don't remember exactly the words. But it was a compelling argument that, according to the religious view, God had created the universe to kind of gravitate and circulate around its creation, which means man and woman, right? Secondary in those days. And then we hit Ptolemy. Ptolemy created a mathematical model that, with very good precision, could not only determine where the planets should be, the visible ones, Mercury, Venus, Mars, Jupiter, Saturn, not Uranus, but up to Saturn. It could predict where they should be, and also could explain changes in brightness of these planets when they were in the process of retrograding. Who remember the difference between prograde and retrograde? Who remember that?
Prograde, they just keep going one way, and then retrograde,
they turn around. In respect to something,
the stars.
That's very important. Because if you eliminate the stars, they all go from east to west. Diurnal motion. Because Earth is going the other way in the sky. But if you keep track of the stars and kind of take pictures, right, of a certain sky region, as Earth rotates, on its axis. So it take a picture of Scorpio, for instance, constellation, the region, and then you take a picture today, tomorrow, the next day, and keep doing that, and then stack all these pictures together. Then you're going to see the planets kind of passing by from west to east in respect to the stars that happen to be in the picture. And then they go, in that progressive way. Moon and the sun always from west to east. But planets, most of the times, go from west to east. Sometimes they stop and turn around, and we call that retrograde motion. How to explain that? And Ptolemy model explained well. How did Ptolemy model explain prograde and retrograde motion? Who remember that?
Epicycles.
Epicycle. So the circular motion was very important. Philosophically speaking, they got this idea that the space was harmonious because always repeats itself. So harmony was up there, and that's why it was a representation of perfection. And the best geometric figure that represents equality, perfection, is the circle with a dot in the center. So if you look at this symbol here, is the symbol of the sun, but also is the symbol of the sun or God's son in various traditions. The circle with a dot in the center, which means the circumference is equidistant from that point anywhere you look. So circular motion should be the motion of the stars in the sky according to this philosophical view, because the circle was the most perfect geometric figure they could conceive. So Ptolemy came with circle. It works okay, but not greatly, especially for Mars. And then it's okay. Planets should go in circle in an epicycle, and then I can explain retrograde. And if even doing that it doesn't work, let's put more epicycles around the epicycles. And it got very complex, to the point that eventually Ptolemy shifted Earth from the center of the universe and put a little bit off, and then improve even more observations and prediction. So basically, it was fudging the idea to the point that couldn't fudge even more, and now we are pretty much hitting 1400, somewhere around that time, when Copernicus came with a different model. Sun in the center, planets go around the sun in circular orbit as well. It didn't work so great. Even geocentric was given better prediction. And then people following Copernicus' idea kept sun in the center, the heliocentric worldview, and create also planetary motions with epicycles, just to improve precision. And then we hit Kepler with his 3 laws of motion. That's how we finished class on Monday. And Kepler was able to explain the motion of planets around the sun, introducing a ellipse as being the exact curve. And then you have a second law of motion and a third, that is an expression. And now we are hitting the second part of the class, which is Newton's law of motion. Before we go there, Galileo Galilei is a very important figure. If you think about science as is structured nowadays, we owe that to Galileo Galilei, because he was the first one that, up to Galileo Galilei, you could come up with hypotheses to explain what you observe in the universe, no problem. So I could, for instance, explain the sun rising in the east and setting in the west by the following idea. Well, the sun is hot, and anything that has heat floats, because I observed that. So the sun starts floating, And as it floats during the day, it transmits heat to all of us. And then lose heat, gets cooler, and then set down in the western sky. And then revigorates itself and comes again the next day. Hypothesis. But that can be tested. So what Galileo Galilei did is to introduce the testing aspect of any hypothesis you can come up in science. The idea of bringing and building up labs that you can create models that represent reality and then test your ideas using these models, pretty much Galileo Galilei did that. And so this is pretty much 1600. And as you are going to see, just using telescope for the first time to spy on astronomical objects. Galileo Galilei didn't invent the telescope, was invented before, but he was the first one who took the telescope and point at the sky and objects in the sky rather than spy on the neighbors or trying to use for military purposes, which he ended up doing and made some good money. But he used telescope to observe sky objects. And that is where our classes start today. So, see if all this works. Yesterday I tried to use these two guys together and they didn't work well for some reason. Let's see today. So far, so good. So, what type of observations Galileo Galilei did? You took a telescope and pointed at Venus. That's the first one. In fact, there was, I don't know if it was the first one, but it was one of them. With that regard, let me show you one thing. So if you go to the Starry Night software, or Stellarium, which is free, and you go to PM, right? So to the evening hours, and then you look to your western sky, and you're gonna find nothing. So which means, let's say 7 o'clock. And look to your western sky. Oh, there you go. And then you find, oh, I'm so sorry. How come no one said that? Are you guys sleeping? How come you didn't tell me the screen was not there?
You thought we knew what you were doing.
What?
You thought you knew what you were doing.
I have my back to the screen. I don't have eyes, you know. Okay, so Starry Night software, we're gonna project. Let me turn off this light here. So Galileo Galilei didn't have a fantastic telescope like we have today. This is 1600. But, I mean, you could see something. For instance, in our physics course, students are supposed to build telescope in a couple of courses. And it's kind of a simple now because we have the proper lens and things like that. But in those days, not so easy. So then you find Venus in the sky. And then you put in the telescope. What does it look like? Yeah, well, in those details here, we can see with ground-based observations. I mean, we know because of probes that have been close to Venus.
It has its own phases.
It has phases. It has freaking phases. And in fact, in the observatory, if you happen to go there, and one of these nights we have public viewing, which is not this Friday, but the next one, looking through the telescope, if you stay around, you're going to see people saying, oh, that's the moon. Because of phases. So basically, the sun is down here, Venus is setting, the sun set before, and the sun is shining on an object that has not proper light, doesn't have proper light. And that's Venus. So Venus here, if you have to advance a phase, don't worry about waxing or waning. Which phase you would call the one? This is tonight, by the way.
Waxing.
It's a waxing. I don't know if you're waxing when. I have to think. Because I have to see how it's progressing. So right now I can't tell. But you use the word gibbous, and I would agree. Gibbous phase. Almost crescent, right? But it's more than crescent. If you take the horns of Venus right here, and then you draw a line. I cannot do in my computer this now, but if you just take a line that goes through the horns right here, dividing the planet in half, I'm not gonna write here either, but you can see it has passed the quarter phase. Call that elongation. Has passed the elongation moment. So it's in a gibbous phase. So Galileo Galilei saw that and got crazy. Why is that? Let me see if that makes sense. I'm going to draw the geocentric worldview. Earth, and then you have the moon, not in order like that, but, and not certainly not aligned, but Earth, and then moon, and then Mercury, and then Venus, and then it comes the sun, and then Mars, and then Jupiter, and then Saturn. That's geocentric worldview. Now, Venus and Mercury, according to this worldview, are always between Earth and the sun. Therefore, moon goes around Earth. But Mercury and Venus are between Earth and the sun. And it's always closer to the sun. So which means ice. So these guys, Mars, Jupiter, and Saturn, are free to go around Earth, according to their worldview, at any given time of the year, so that sometimes, let me erase so that sometimes you might find Mars right here, or Jupiter might be right here, and Saturn might be there, no problem. Same thing with the sun. Sun can go over here. But in the sky, when you observe Mercury and Venus, they are always tied up to the sun. They are always close to the sun. For instance, Venus now is close to the sun. The sun set and Venus set too. the sun is going to rise the next day, and then right after, Venus rises too. But it's going to be daytime. You can't see Venus. Same thing with Mercury. Mercury is even closer to the sun. That's why the symbol of Mercury in Renaissance was what? Who came across that information? The symbol of Mercury in Renaissance is an animal. Start with M. No, I'm sorry. Start with not with the G, with the R. Rooster. Why is that? What rooster do? They announce the sun rising. I have one in my neighbor. So the sun is about to rise, and I'm hearing this guy, calling the sun. And then in the mythology, Mercury becomes the messenger of sun god, because it's announcing it's coming. That's the mythology thing. So Mercury is always close to the sun. The sun sets, that's when you can see Mercury in the sky. Or now Mercury, orbits the sun. Mercury rises early in the morning before the sun rises, and then you can see it. So to match this observation with the model, what the geocentric people did was to keep, and I will eliminate the other planets because the other planets could go around the Earth at any time. They force Mercury and Venus to be going around their deferent, remember that? But the deferent was tied to this line connecting Earth and the sleeping, or checking what's going to do in the weekend, or reading text message, which people do a lot when they are driving. It's so crazy. I drive Highway 17, and it gets sometimes stuck, and there's always everybody checking something. Okay, what's going on here? I don't know how they can do that. So because these two planets are tied to a line connecting sun, this is sun, and this is Earth, according to the geocentric worldview. Which phase you can only see them in the sky? What is the phase, the only phase that you could see them in the sky? You could see in the new phase. You could see what? In a crescent phase? Could you see in a gibbous phase? Not at all. Could you see them in a full phase? Not at all. Because in a full phase, you would require Venus to be here. In a gibbous, Venus must be here or there. Mercury has to be. So the most you can see maybe is close to quarter, but never in a gibbous phase. So geocentric worldview, as proposed by Ptolemy, had this little thing that if somebody could look at the planet, could certify the model doesn't work. That's what Galileo Galilei did. He said, well, I'm going to get this instrument that, forgot the name of the Italian guy who invented, and then point at Venus. And he followed Venus. And then certain enough, like coincidentally today, Venus is in a gibbous phase. And according to the geocentric worldview, this will not happen. And that is the power of science. So you have a model that predicts things. You have a geocentric model that predicts Venus and Mercury not to be in a gibbous phase. And then you observe it. And then what you do, you talk to Mother Nature. Please open your books. Reveal to me your secrets. And then when you look at, when you dialogue, establish this communication, and then you find, oops, this model is not working. And they say, the model is wrong. Now, there was a person named Tycho Brahe, and he knew about that, and then he took the geocentric worldview, and he built a model which was a geocentric, so Earth is still in the center, but he allowed Venus to orbit the sun. He allowed Mercury to orbit the sun. And then he hired Kepler, Johann Kepler, to prove his model to be okay, to check the mathematics of it. But he died, as I mentioned last class, and that couldn't be done. Now, let's take the Starry Night software on another trip, and at this time, let's go to the morning hours, to the wee hours, 3 in the morning, 3 a.m. Even the sucking rooster is sleeping at this time. And let me bring the ecliptic here so I know, excuse me, where to look at. And is this here? Spike 5. No, it's Scorpio. Where is Jupiter? Oh, that's bad. Okay, Jupiter is right there. Okay, so let's do the same thing and look at Jupiter. And for now, I need some juice here before everything's crashed down. Okay, we are approaching Jupiter. It's there. Let's kind of reduce a little bit. Let's center. Oh, it's already center. And let's speed up time. In fact, let's go. See, we are blasting off, getting around Earth atmosphere. There you go. Jupiter is there. So there are some objects here. Let me take the labels out. There is some little thing here that looks like stars. And let's run the time. Take this line away. Let's speed up even more. I don't like that. Let's go to a different location. Sorry about that. Should have thought about this before. Let's just do one thing. Let's go to North Pole. And blast off. And use labels here just to help me locate where they are. Can you see Jupiter's? Oh, there you go. Jupiter's there. Center. And take the labels off. That's Jupiter right there. And let's approach Jupiter. What did I see? What did I find there? Jupiter's here. Okay, that's better. That's Mr. Jupiter. Let's reduce a little bit. And now let's pretend to be Galileo Galilei, and that's too fast. You get it right. Just take some time. And keep observing Jupiter if we could. Still too fast. Maybe that. Okay, this is better. So, can you please find out what's going on here? So Jupiter is rotating, right, on its axis of rotation. So probably, I don't think Galileo Galilei could see these definitions. In fact, if you go to our observatory, not now because Jupiter is only visible, and there's something cool that happened in there. It's only visible, 2, 3, 4 in the morning, 5 in the morning. So we can't see those. We can see the bands. We can see there are 2 bands, but we can't see a lot of detail in there. So, but Galileo could see Jupiter and could see the stars too. So since we are running time, we have the stars passing by, which in other words, Jupiter is going that way in respect to the stars. Jupiter is prograding. But there is something else going on here. Can you find it? Can you help me to locate? Look at this thing over here. And it's casting shadow. See that? And look at another one casting shadow right here. And then let's keep going. There's another thing over there casting shadow, I think. And now it's going back. There's another one here. I don't know if that is a star. Looks like a star, maybe. I don't know. It's moving like other stars are moving. But that one certainly is going. Oh, look at that. Look what this guy is doing. It's thinking twice if it should go that way. And look at that. I'm not moving my finger, I swear. Now this guy's going away. This object here was in front of Jupiter. So Galileo Galilei pointed at Jupiter and found what today we call Galilean moons. He found Callisto, Amalthea, Adrastea couldn't be seen in those days, but he found Callisto, Ganymede, Io, and Europa. 4 Galilean moons, which he interpreted as being Galilean moons. That's Galileo. He interpreted as being moons because he thought, okay, these 4, which looks like stars, as you look in the telescope, are in fact going around Jupiter, because he has a table, Jupiter, 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 Jupiter. And then what he found was at different times he observed these moons were positioned differently. These stars were positioned differently. So he came up with the following argument. Well, I found 4 objects that are not going around Earth, because what the geocentric and church in those days were saying was that everything in the universe must go around Earth. And he said, hey, can you open the door? I found 4 that are not going around Earth. And because of that, he got house arrest. Or, he had to abdicate from his view, because he said, okay, not all the objects go around Earth. He had to decline that was not true, or he would be killed. He would be burned, as heretical or something. So he got in house arrest, and then he took his time observing the sun now, to the point that late in his life he was blind. So do not ever look straight at the sun, because it's going to burn your retina, and you're going to get blind. He also found in the sun had spots, sunspots. So let's visit another part of our sky. Let's freeze the time and bring daylight, high daylight. Go to AM. And get out, going back to Earth. Sun is there, center. Right here, maybe? I don't know. Maybe there's the sun. Magnify. And then if you observe the sun with the good filter, you are to find a lot of blemishes, spots, sunspots. Depending on which time of the year we observe, probably if we do this exercise now, the sun has no spots. And this was against the idea that whatever was out there above the moon was perfect, harmonious, without blemishes. God's creation. And because God's perfection and absolute, everything that He creates should be absolute and perfect, except everything else below the moon. When you look at the moon, you see blemishes, right? Maria, as we know now. But in those days, so the world of transformation, the world of becoming, was the so-called sublunar world where we are, which were controlled by, according to them, the elements, earth, water, air, and fire. So combination of that gives rise to decay and transformation as we observe in our lives and on earth. That was their philosophical approach to explain differences. And now we know transformation, decay, and becoming is not only here on earth or the moon, it's everywhere in the universe. The stars, they merge, they migrate, they collide, galaxies do the same, and they transform themselves. The universe as a whole is becoming chemically more rich than it was the day before, because the stars are dying and polluting the interstellar medium with newly formed atoms. So the universe is in transformation all the time. Now we know. But not in those days, where science was primarily being guided by philosophical or religious worldviews. Okay, get out of here, and let's go to back to Galileo Galilei. That is Venus in a gibbous phase. And now you know this can't be a fact. Now, Galilei came up with the laws of motion. That's why I brought this little kind of a trick here. And that will bound to Newton's laws of motion, and I will go together here. And I would like to warn you that chapter 3, I don't know about homework. You might have a lot of homework questions that has to do with the physics of Newton's law. And quite honest, I'm not going to go there. And I will try to screen the midterm from those questions. But basically, I want to arrive at this equation. This is what I want you to pay attention to. Is the equation according to Isaac Newton that gives rise to the notion of force, gravitational force, and what gravity exactly is. Gravity is one of the four major forces that rule out nature, and gravity has the importance of being local because we feel gravity. I jump and gravity pulls my body back to the ground, But gravity is also a force that has action over very long distances. The distance of not only stars, but the distance of the space in between galaxies. Let me start with the first law of Newton. It's a law that is not pretty much meeting our common sense. The first law of motion says if you have an object that moves with constant velocity, that object will keep moving with constant velocity forever and ever unless there is some external force acting on it that takes it out of balance. And then goes to the second law of motion, that external net force must be proportional to the change in velocity over time. We call that acceleration. Again, we spend weeks learning that in physics, and I don't expect you in 30 minutes to get it. But let's see if it makes sense what I'm going to show here. So I have a flower, and I have a cart. So I'm not going to do with the flower because it makes a big mess, especially with the dark type of clothes here. I don't want to be funny when I get out of here. But imagine that I sprinkle flowers all over the place and I try to make my cart move. So do you think the car is going to move easily through the flower? Right? It will not. Because the flower will somehow hold on the movement of the car. According to Newton, if I am able to eliminate all possible resistant forces, and so now I have a car that has very nice rotating wheels. Let's say I have a track that is so well balanced, as you can see here. It's not. If I give a little tap on the car, according to Newton's first law of motion, the car would be moving forever and ever and ever with the same velocity all the time. Do you think this is going to happen? No, it stopped. Why did it stop? Because of something in physics we call, start with F. No, it's not what you're thinking.
Friction.
Friction. It's friction. So, but then you say, well, I'm going to get some oil and I polish this, polish. And then let's do again. And believe me, it still stops because friction doesn't go away. At the atomic level, you have electronic interactions that resist the motion of the cars. So friction is everywhere, right? But according to Newton, if ideally you don't have any friction, your car will just keep on moving. That is the first law of motion, which gives rise to something called inertial mass, which I'm not going to go there. And the second law is, well, if it stops, it's because there is a resistant force that is proportional to the change in velocity of that car over time. So, and the third law of Newton is law which I like to call karma in physics. It's pretty much mechanical. If you exert an action in some object, that object exerts a reaction on you with the same intensity but opposite direction. It's like karma thing, right? Almost the same. If you have two players boxing and hitting one another, there is not a winner because the amount of punch that one receives, the same amount of punch the other receives, but in opposite directions and in different parts, body parts, which makes a big difference, right? I don't mind to hit my knuckle somewhere, but I do mind to hit my chin somewhere, right? Because this sensitivity of certain body parts. So those are the three laws of motions you might see in your homework. If you do, and if you get complicated, make sure you contact me, and then we can work together. Good? Cool? But I'm not going to go in a lot of details. Now, these three laws of motions led Newton to this important equation, and that's what I would like to spend more time. So force is something that push or pull. So you can push some block or it can, like I was teenager, my car or my friend's car would quite often and magically finish its gasoline in weird places. And then we have to push the car up to the station or wait for some good soul Samaritan to come and give us gasoline, which we would suck and take out of the tank. Now we can't. It's kind of a difficult. I haven't tried though. But you would put a tube in the French tank and suck gasoline in before the gasoline would go to your mouth. And most of the times it would go to your mouth and it would spit out. And then you would put gasoline in a tank and then go to your car and then fill it. I mean, 18, 19 years old. That's what you do at 2 in the morning. And so that's a pushing motion. Now, pulling force is the one that cables do on car. So you attach a cable to a car and then you pull that thing. So the force, push or pulling, are responsible for changing the state of motion of those objects. So everything goes now everywhere. Where I was. Okay. I don't know where I was. Okay, so gravity is a... Yes, thank you.
What is the R? What's the difference between the R and the D in the formula behind you?
Between R and what?
The other formula, you have a D.
Oh, it's the same.
Oh.
Yeah. D for distance, R for distance too. Thank you. So the reading we should do of this formula is the following. The gravity force that keeps the moon attached to Earth, that keeps Earth attached to the sun, that glues the solar system all together, that gravity force depends on a constant, which is very small, by the way. It's 10 to minus 11. It's a very small number. Multiplied by the mass of the bodies, the mass of the objects, multiplied, as you can see, divided by the square of the distance between these two objects. And then you might think, okay, I can see the moon. What is the gravity force of the moon on Earth? Okay, well, I take this number here, which is very small, right? About 10 to minus 11. And I take the mass of Earth. I take the mass of moon in kilograms, by the way, right? And I multiply them. For instance, just to give an idea, my mass in good days is about 80 kilograms. 80 kilograms. Let's say our mass, the mass of each one of us, just to give a number, is 100 kilograms. And then you take our mass and multiply by the mass of Earth, which is quite massive. And so what would be the distance here in this equation to exemplify the gravity force that keeps me attached to Earth? Well, it's the distance from the point I am to the center of planet Earth, which is Earth's radius, about 6,000 kilometers. So when you take these numbers and plug it in there, you have the value of the gravity force that keeps me attached to Earth. And then you stop and think, hey, I'm sitting next to a classmate. How come we are not glued together? How come all of us here suddenly don't get crunched together and form a big, massive GUI of human bodies? Well, it's because this G here is a very small number. If you plug here your mass and your mass, the distance between two of you, which is 1 meter, and multiplied by 10 to minus 11, the value of the force is totally negligible. You guys ignore one another. And the force, the electronic force that keeps you kind of attached to your clothes, and the gravity force that keeps you attached to the ground, and all the other force, psychological attraction or reaction or repulsion you have to certain things, are more important in our everyday life. We see the moon acting on us on tides, right? This gravity force is able to pull ocean masses high a little bit, and then you go to Santa Cruz and we have good time in tide pools and things like that, right? So you can see the effect of gravity on Earth that way. So I'm going to jump all of that because, again, it has to do with um, with physics. And again, if you want to go deep on that, I'm very happy to work with you. So Newton's third law is action and reaction. So here in blue, you can see you have a moon and you have Earth. This blue force here has the same intensity. The intensity is the same. So which means if I calculate the force in which Earth attracts me down, is the same force that my body, attracts Earth upward. So when there is this attraction, there is also acceleration, which means the objects tend to move towards one another. In long time, like 10 million years, then objects in the space, they ended up getting together, but takes time. And here in green is a temperature represents that acceleration. So acceleration is bigger for the smaller object and much smaller for the bigger object. In other words, the acceleration in which I fall to the ground is a number close to 10, 9.8 meters per square second, but Earth acceleration towards me is negligible number. Again, honestly, I don't accept you get all of that unless you studied physics before. But for you, this is the important part. I want you to build this notion that things will attract one another and will depend somehow on the distance. If they are too far apart, the gravity between them is less than it is when they are closer, because the distance happens to be in the denominator. Also, if the objects are massive, then the gravity force will grow accordingly because we have a multiplicative factor to consider in there. So G is the acceleration that I have here on Earth. If I go to the moon, the acceleration is 1/6 of what it is here. So which means if I go to the moon and stand on a scale, I will feel lighter, right? There will be less pulling force to the scale, so the scale will read something better, in my opinion, than it would read down here. And Mars is 1/3 of this. So the gravity in Mars is bigger than the gravity in the moon, but it's less than the gravity here on Earth because of masses, the mass of this object. So this is the important thing that I would like you to play around. And the last thing that I would like to show here is the notion of orbital motion. So what does it mean when the moon goes around Earth? What does it mean when satellites, artificial satellites, handmade satellites orbit Earth? Exactly what's going on? Well, so here's a simple example. You take a cannonball and you take a blow. And we don't need to have a cannonball. I can throw anything. So I'm going to take this eraser and throw, and you see it's curves. We call this pattern a parabola. So why it curves down? Because here in green, as you can see, there is a force, which is gravity, that is pulling this cannonball or my eraser down. So there is a motion forward, but there is also a force pulling it down. When you combine these two effects, the fact that there is a forward motion that is somewhat uniform, but you also have a pulling down force that changes the velocity in that direction. When you combine these two effects, we have this nice, beautiful parabola. So let's say that I do a lot of push-ups, and tomorrow I repeat this class, and I have a little bit more of muscle, and I can throw this eraser a little bit further. Do exercise, go further. So every time that we do, I send it further. Also, let's assume there is not such a thing called what? that we need for survival?
Oxygen.
Oxygen or
Air.
air. Let's imagine we don't have atmosphere. There's no air resistance. So you throw something, and that thing just keep on going without resistance. And I have so much strength that I can throw in such a way that never falls. As it tries to fall, it follows Earth curvature. It's kind of a crazy if you think, right? But it's possible. It's not impossible. Eliminate atmosphere and bring a superwoman here that can do these things, and this is going to happen. And then you have what's called orbital motion, right? So you put something in orbit. So you put something in orbit in any planet, in any system, as long as you're able to launch with what's called escape velocity. Is the velocity required or the speed required to overcome gravity in a way? And for Earth is about 11 kilometers per second. So it's about 7 miles per second. Just think about it. 7 miles. 7 miles is from here to where? To Highway 101, maybe? Maybe 7 miles? More or less? Who goes to Highway 101? So it's 4 miles, no? 4 miles? So it's more like San Jose State is how many miles? San Jose State? Maybe? In 1 second. That's what you need to get out of here and not come back. So, if you throw something up in the air, it's going to come back. Okay? Gravity will pull back. Let me stop here and just allow your mind to go on the big scale, the scale of the universe, Big Bang. And we will discuss this later towards the end of the course, but imagine, and this was pretty much stated in chapter 1, 13.7 billion years ago, there was a major sudden expansion in space-time. And this expansion led to creation of matter, as we have here, this stuff. And later on, we're going to learn this is what we see, all these beautiful galaxies and everything, 5% of the universe in terms of energy. And this is expanding. So in the 60s and 70s, we know the expansion is going on because we can measure with Doppler effect, and we're going to learn that stuff. But there was a following question. Well, if the universe has enough mass, so eventually this expansion would stop and everything would come back to a big crunch. The big crunch. So you have the Big Bang, you have the big crunch, right? And there was a major debate because of gravity effect over long range, because of that 1 over r squared. And this discussion now is kind of muffled because what we observe is the expansion seems to going in a very smooth and flat way. And this returning might not happen. And then in 20 years ago, they found the dark energy that is speeding up. Like you throw the mark up in the air, and instead of having the mark slowing down, you observed, in fact, it's speeding up, going upward, which makes no sense. That's why they create this term dark energy. So if you read before about it, it's one exciting front of science, especially astronomy, that is being investigated. But according to Newton's law, we then go to the point of orbital motion as a result of the action of gravity. So what is the important takeaway message of today's class is basically the action of gravity pulling things together. Gravity is always contracting and pulling in force. And I have some videos here that I select and I would like to show it to you. Let's start with stars that exchange material. So what you're seeing here is a system called cataclysmic variable. Cataclysmic variable is a star that is inflating and getting to the point that the gravity of a compact star, could be a white dwarf in general, is, sorry, what do I do? Right here. And let me stop here. So this is a binary star. So they were formed together, so they have the same age. But we will start later that massive stars, stars that have a lot of content, they evolve faster than those that don't have a lot of content. Like high mass objects live shorter than low mass objects in the sky. So this star here is a high mass star. Is a low mass star. In fact, lower than this star over here. This star over here is gone and is pretty much represented by a collapsed and evolved object in the very core, because most of its external material has been lost. It's a white dwarf. Don't worry about it. I'm just saying things we are going to learn in about a month. So it's a white dwarf that has some disk around, some material around, because this companion, its sibling, that now start to evolve and expand, is transferring material to the system. And why is being transferring material? Is there a love story in the cosmos? Are they kind of connected in some kind of a spiritual way? That's gravity. So gravity attracts the two objects and keeps them together. But it might reach a point when the star inflates itself to a point that this attraction is able to bring material, to capture material, and transfer material from one system to the other. And then this circumstellar or circum white dwarf disk start to be formed. And so when these processes happen, a lot of emission and brightness and flares is pretty much detected. And pretty much that's what the animation is trying to show. Is an example of gravity as it acts in a couple of stars. Okay. Now, neutron stars are collapsed objects from very massive stars. Massive stars, and we will learn them, more than 10 times the mass of our sun. When they die, their central part can become what is called a neutron star or a black hole. So it might happen that two binary systems, they evolve to explode as supernovae, and their core, neutron star, now orbit one another. And what happened when these two neutron stars collide with one another?
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma-ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma-ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging stars into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows two neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic.
I mean, if you want to follow the rest of the simulation, you can go to the video I will upload and take a look. But the main point is to show how, again, gravity is acting on a system of two massive stars, in fact, two collapsed cores. Now, let's increase even more the size of the system and look at galaxy interaction. So this is a nice simulation that also includes gravity, but not gravity between two objects, but hundreds of billions of objects. So you have two galaxies interacting because of the global gravity between them. And the simulation was done in such a way that every single segment of the simulation try to show configurations that are in fact observed. So this is a picture of an observed system. That is a simulation, it's not real. And then the simulation is going to go, and this is a real picture of two galaxies interacting. So galaxies, hundreds of billions of stars, can only interact that way because of the gravitational effects that one has on another. And in this case, you have two spiral galaxies interacting, and as they do interact, you see the development of spiral arms that are so conspicuous in this type of system. And then again, another observation that might have been produced by this type of interaction. And the last one is our Milky Way galaxy and Andromeda. So our Milky Way galaxy, which is the galaxy we live, is in route of collision with Andromeda galaxy. In 3.5 billion years or so, these two galaxies will merge, and if we are still living 3.5 billion years from now, instead of having just a Milky Way galaxy going across the sky, we're going to have another beautiful one, Andromeda galaxy, also going across the sky. And this simulation indicates what that might look like based on what we know of their proper motion. As they get close to one another, observe the development of spiral arms. There is a satellite galaxy in there. It's a three-body system, sort of. When galaxies collide, stars will not collide because stars are too much far apart. Gas between stars is populated, gas populates the region between stars, and gas will collide. Gas will heat up. And as a result of this gas collision, more stars, baby stars, might be formed. But that is the result of interaction of our Milky Way galaxy with Andromeda galaxy. 3.5 billion years. All right, fellows. This is chapter 3. Homework is due next week. Keep on track of that. This chapter has a couple of extra credits, so make sure you do it. And have a great weekend.